All right, moving on to lecture 9, force problem examples. We've got a bunch of examples that we can do here. Here's our first example. Now, one thing that I've done with these examples is I give you a bunch of potential questions to look at before you actually solve anything. And so I don't actually give you a question to look at quite yet. I just say, okay, the box has a mass of 7 kilograms. All right. Well, you see a force acting on that object. You can kind of start guessing that there's going to be free body diagrams involved here. You know, okay, there's masses, there's forces. There's probably going to be a free body diagram they're going to have to draw. We can start considering certain things. What is the acceleration of the box in the y direction? Think about that for a second. What is the acceleration of that box in the y direction? Yeah, I see it in chat. It's 0. That box had better not be accelerating in the y direction, or it's going to be falling either through the table or it's going to be leaping off the table. And neither of those is a reasonable thing for that box to do. Therefore, if that box is not moving up or down, then we can presume that the acceleration of that box is 0 in the y direction. That's not necessarily going to be the case in the x direction. If we're pushing on that box like that, it might start moving. It hopefully will start moving in the x direction, but not in the y direction. Another question, this is a question to think about before you actually solve anything. I haven't even told you what the real question is for this example problem. This is just another question to think about before you even start off solving anything. This is one method for solving problems, to just ask yourself a bunch of questions about the setup of the question before you actually look at what the question is asking for. What forces act in the y direction? I will give you, I'll give you 30 seconds to think about what forces are acting in the y direction. Yeah, I see some stuff in chat. In the y direction, we definitely have gravity. Technically, that's in the negative y direction, but who's counting? We still call it in the y direction. It's just going in negative y. So we'd have to remember to add a negative sign in there. We've got the normal force, which is pushing up out of the table to keep the block from falling through the table. And we've got the hand. You know, that hand, that applied force, is not pushing only in the y direction, but a component of that applied force from that hand is in the y direction. That applied force is somewhat in y and somewhat in x. So the y direction has 3 forces acting in it. Up is going to be normal, down is going to be gravity, and there's going to be a component down from the force from that hand. So normal, gravity, and a component of the applied force are acting in the y direction. Always good to think about these things. Is the magnitude of the normal force equal to the mass of the object times the acceleration due to gravity? Now, given what we just said, we have said 2 things. One thing that we said is that the acceleration in the y direction is 0. And we have also said that there are 3 forces acting on this object in the y direction. One that's going up is the normal force, and 2 that are going down are gravity and the y component of the applied force. Therefore, is the magnitude of the normal force equal to the magnitude of mass times the acceleration due to gravity? Think about that for a little bit. The correct answer is no. the magnitude of the normal force is not going to be exactly equal to the mass times the gravity. And the best way to talk about this is probably to show you. I have drawn here the setup, and I've drawn here a free body diagram for this setup. We've got the applied force coming in at an angle. We've got the normal force pointing up and the force of gravity pointing down. Imagine if the force applied was absolutely ridiculously huge. Like, let's have a diamond table or something like that that can definitely withstand any kind of pressure being put on it. And so let's have a ridiculously large force pushing down there. Well, if we have a ridiculously large force pushing at that kind of diagonal, then we're going to have a ridiculously large downward component of that force. And so the normal force would have to be a lot more than the force of gravity. If it is not, then if the normal force is not larger than the force of gravity, the magnitude of the normal force is not larger than the force of gravity, then you're going to have more force down than force up, and that would cause the object to fall through the table. Remember, if the forces are not balanced, then you're going to have an acceleration. If the net force is not zero, you will have acceleration. We have said there is no acceleration on this box. Therefore, all the forces up have to equal all the forces down on it in the y direction. We're only talking about the acceleration in the y direction so far. Let's actually first look at what's going on in the x direction, because that's actually a little bit easier to look at. The net force in x, so F net x means net force in x, is equal to the mass times the acceleration in x. Looking at this, it looks like we're going to be accelerating that way, and so we can have a positive acceleration, and so we don't have to deal with a weird negative there. What are all the forces acting in the x direction? Well, normal doesn't act in x, gravity doesn't act in x, but a component of the force applied acts in x. So I can say that F net x is all the forces acting in positive x minus all the forces acting in negative x. Well, there's only one force in x at all, and it's the component of the force applied, the x component of the force applied, and that's going in a direction we usually call forward. So the force applied in the x direction is equal to max from there. The x component of the force applied is going to be the force applied times the cosine of 45. We're told that's a 45-degree angle, and the x direction is almost always cosine. We will do a problem where that's not true soon enough. And so we've got this force applied times cosine of 45 is equal to max. We can ask our calculator what cosine of 45 is, and we can look back at our problem, seeing that that's a 10 Newton force right there, and say, oh, well, it's 7.07. 10 times cosine of 45 is 7.07. The mass I told you was 7 kilograms, so 7.07 is equal to 7 times ax. Ax is equal to 1.01 meters per second squared. If I was just asking you for the acceleration, which I suppose I was just asking you for the acceleration in this problem, you could end there. You don't even have to look at what's going on in the y direction. You can just say, oh, the acceleration in x is 1.01 meters per second squared, and there's no acceleration in y because, well, it's not falling through the table. On the other hand, what if I asked you, what's the normal force on that block? You know, what's the magnitude of that normal force? Well, what you can do is set up the exact same thing. F net y is equal to may. May is 0 because ay is 0. So F net y is equal to 0. What is F net y made of? Well, it's made of all the positive forces in the y direction minus all the negative forces in the y direction. That's going to be positive normal. So it's going to be normal. That's the only thing going in the positive direction, in the up direction. And so we have to subtract off everything going on in the negative direction, the down direction. So, okay, normal goes up. Going down is force of gravity. So we'll have to subtract off force of gravity. And going down is the applied force, or the y component of the applied force. So we can replace that. We can say that F net y, all the positives minus all the negatives. Positive is normal, minus force of gravity, minus force applied sine theta. That's the y component of the force applied right there. You see that I have the positive forces minus each of the negative forces. So there's multiple minus signs. Don't have a plus there, because then you're adding back in that force, and that'll get you the wrong answer. So don't do that. We can do some algebra on that and say that the normal force is equal to the force of gravity plus the applied force times sine of theta. And then we can say normal force is equal to mg, which is the force of gravity, plus force applied, which is 10, times the sine of theta, which is 45. Ask our calculator, it's 7.07, which was the same as the cosine of 45. Sine of 45 and cosine of 45 are the same, so it's not surprising we see that number again. And then we can say, oh, the mass was whatever, the gravity is 9.8. Add them together, you get 75.7 newtons up for the normal force. Any questions on this example problem? Why use 45 degrees if it's 135 degrees from the perspective of the box? Oh, we're using that direction. If we're using that direction as the direction from which you measure all angles, which, hey, I did say that that's the best thing to do. Well, then you can say that angle there is 135 degrees. That's correct. But there's another way of thinking about this, and this actually might annoy people, thinking about it in all these different ways. The way that I really recommend you think about it is just taking apart any vector that you see into its components. So if you're more mathematically inclined, you can also think about it like this. We're pushing in like that. So actually the angle we should be using is this angle. We should be saying that the angle of that force is negative 45 degrees because it's pushing in like that, which is down and to the right. So if you plug in negative 45 degrees there, you'll actually get the exact same answer. If you plug in negative 45 degrees there, you would get a negative answer, but we already accounted for how it's negative by putting that negative sign in there. And so it ended up not mattering. The important thing that you do here is that you think about these in terms of their vectors. You think about each diagonal looking vector and you break it up into its component vectors. And I'll actually show that here. My force applied is going to be one vector like that and another vector like that. That is the FAX and FAY vectors there. If you can break it up into vectors, then it becomes a lot easier to see what you're doing. And so I recommend that you do this kind of thing. FAX, well, it's just going to be a positive number. So set it up so that you get a positive number. FAY is going to give you a negative number. I forced that issue by adding that negative sign there, by saying, oh, it points down, therefore I'll give it that negative sign. If you left this as positive, then you'd need to treat that as a negative 45 degree angle right there to account for how it's going down. I understand that a lot of people don't like having that kind of ambiguity in a problem like this, where I say, well, yeah, you could do it either way. I get that, but it's very important that you be able to think like that, because when you're an engineer or a physicist or a chemical engineer or an aerospace engineer or whatever else anyone in this class is doing, you'll be given problems with ambiguities. So learning how to deal with those ambiguities right now and saying, oh, I can either leave this as a negative and just have a positive angle, or I can make it positive and have a negative because I know that it's pointing down because I've drawn it out. Learning to do that now will help you immensely in your career. So I strongly recommend that you get used to this kind of thing. Eventually, I do ask the question, find the normal force and the acceleration on the block. And so our efforts were not wasted. We found both of those. And I give you the answer, and I give you the work for it just so you can go back and peruse it at your leisure. Here's another example with two movers pushing a box across the floor. This is an overhead view of what's going on. The box has a mass of 90 kilograms. Will the box move exactly along the x-axis? I suppose we don't quite have time for the question part, but that's something to think about. Will the box move exactly along the x-axis? This is an overhead view, so it's not like the y-axis, moving on the y-axis would cause it to fall through the floor or the table or something. This is an overhead view. You can actually have acceleration in x and in y. So really, we don't know if it's going to be accelerating in exactly what direction without doing all the math. It's probably, looking at the forces here, we've got two pretty substantial forces, each with an x component, positive x component. So yeah, it's probably going to be mostly accelerating in x, but it could also be accelerating in y. I'm not sure, just by looking at it, which y component is going to be greater. Now, if we break up each of these vectors, f1 and f2, into their components, well, f1 has a pretty substantial x component and a pretty substantial y component. f2 has a very substantial x component and a pretty substantial negative y component. I don't know if the magnitude of the y component for f1 is greater than or less than or equal to the magnitudes, just looking at the magnitudes of the y component for the force f2. I don't know myself. That means that we probably have to do math. At what direction does it move, and at what acceleration? I again have the setup that I've given you here, just redrawn it, kind of small. Tell you to find the acceleration. The acceleration is both the magnitude of the acceleration and the angle of the acceleration, because it's a vector, and vectors are always magnitude and direction. So we can just start with something, and I'm going to start with x, because why not? You can kind of pick whichever one you want. You can pick x, you can pick y, it doesn't really matter. Whatever you want to start with. And you can say the net force in x is equal to max. Well, it certainly looks like it's going to be accelerating that way, so we can give it a positive amount there, just by not giving it a negative. What are the things pushing it in the x direction? What is f net x made out of? Well, we've got that x component of a, or 1, whatever, however we're labeling it, and the x component of this other one. Both of them have an x component. So the net force is just going to be the two x components added together, because they're both going forward. So we get that. Fax is plus fbx, or the force, the x component of this force plus the x component of this force, is still going to equal max, as we would expect. We then just need to figure out what the x component of this one is and what the x component of this one is. That's not bad. X component of that one is going to be f cosine theta, and x component of that one is going to be f cosine theta. Well, the force of this one was 100 newtons, so 100 cosine theta was 60 degrees. And for the second one, f 140 cosine 30 degrees. Note here that, yeah, maybe it should be negative 30, but cosine of 30 is equal to cosine of negative 30, so it doesn't matter if you have a positive or negative there. This is, again, what a lot of people get annoyed by. the ambiguity of what angle to, or what sign to give angles. That's why it's so vital that you understand the unit circle and remember the unit circle stuff. So you can remember, oh yeah, positive 30, negative 30, it doesn't matter for cosine. For sine, it definitely does, but not for cosine. Well, that's still equal to max. And these are all just numbers. Ask your calculator. It's 90 kilograms, so you can just solve for A algebraically, and you get 1.9 meters per second squared. Done. Okay. For question, how come some of those equations aren't on the formula sheet? If you're talking about, actually, can you tell me which equation is not on the formula sheet? This one. Well, this is an equation that only works for this problem. If I gave you that equation on the formula sheet, it would not help you on any problem except this. This is an equation that we created for this problem. Remember my discussion of what makes physics. Physics is not just plugging numbers into equations. Physics is creating equations. This is an equation we created for this situation. We said F net x is the net force in the x direction, and that net force in the x direction is created by adding the x component of force A and the x component of force B. That is only true in this situation and in any sufficiently similar situations. But giving you equations like that would not actually help for any other situation. It would only serve to confuse. One of the most important things in this class is to learn how to create equations from other equations and from situations like this. That is absolutely vitally important for success in this class. And so if you have concerns about that, then please email me or talk to me after class or something. Yeah, I see in chat the sum of the forces is equal to MA. You have to take the sum of the forces and you have to recognize, okay, the sum of the forces in a particular direction, well, I just add up the components. Because that's why we learned vector addition earlier on in the semester. We can do the exact same thing with y. F net y is equal to MAY. Well, likewise, F net y is going to be all the y components added together. And I know that the y component of A is pointing up, and we're going to take that, or it's not really pointing up, it's pointing up on this paper, but we're going to define that way as being the positive direction. Remember, this is the a view from above. And so we've got a positive y component and a negative y component from B. So I'm going to take the positive y component minus the negative y component like that, equal to MAY. And because this is the net force. Yeah, remember from last time, net, just like net income, is all of your positives. Well, you see a positive component for that y and a negative component for that in y. Well, you got all your positives minus all your negatives, all your incomes minus all of your expenses, all your bank accounts minus all of your loans, whatever. The net force, the sum of the forces, and that is equal to still MAY. Then we can replace those with the components, and that's still going to be 100, the force times the sine of theta minus force times sine of theta. We just plug in the forces and thetas. Again, we could make that a negative, but then we know that sine of a negative value gives you a negative amount, and we are already taking care of that negative amount with that negative sign right there. So remember back to your trig so that you can do that kind of thing without even thinking about it. That's equal to MAX. And then these are all just numbers, so we solve for the numbers. And we get that AY is equal to 0.184 meters per second squared. So it's predominantly going in the x direction, in the positive x, but it's also going very, very slightly in the positive y direction, which someone said in chat, so that's great. Then, if we want to find the magnitude of the acceleration, we can use the Pythagorean theorem, like that. We take this squared plus this squared, take the square root, and that gets you the acceleration like that. And notice that it's pretty much just a little bit more than that. And then we can find the angle, and this was, I didn't write it down, but this is from the inverse tangent of AY over AX. That's how I got that right there.